let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through the cosmos, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide. We're going to follow two spacecraft on the longest journey ever undertaken, a voyage that has stretched across nearly half a century and continues tonight as you listen, as they travel through the darkness between stars. These are stories of discovery, of human courage and ingenuity, of messages sent across the void, and of machines that have become, in their own way, a testament to what we can achieve when we dare to look beyond ourselves. So, breathe, relax, and let's drift together into the story of Voyager, two spacecraft that left Earth when your parents or grandparents were young, and which are still traveling right now into the endless night. The launch and the grand tour. In the summer of 1977, the world was a different place. Elvis Presley would pass away that August. Star Wars had just opened in theaters, capturing imaginations with its vision of a galaxy far, far away. The first Apple II computer went on sale, and at Cape Canaveral in Florida, NASA was preparing to launch two spacecraft on a journey that would redefine humanity's understanding of the outer solar system and, eventually, take us beyond the realm of the sun itself. The story of Voyager really begins in 1964, in the offices of the Jet Propulsion Laboratory in Pasadena, California. A young aerospace engineer named Gary Flandreau was working on trajectory calculations, plotting possible paths for future missions to the outer planets. As he worked through the mathematics, he noticed something extraordinary. In the late 1970s, the giant planets of the outer solar system, Jupiter, Saturn, Uranus, and Neptune, would align in a way that happens only once every 175 years. This alignment meant that a spacecraft could visit all four planets in a single mission, using the gravity of each planet to slingshot it onward to the next, like a cosmic billiard shot that bounced from planet to planet. This technique, called gravitational assist or gravity assist, had been proposed theoretically but never demonstrated on such a grand scale. The idea was elegantly simple. As a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it gets closer. If the trajectory is calculated correctly, the spacecraft swings around the planet and is flung back out in a new direction, having stolen a tiny fraction of the planet's orbital momentum. To the spacecraft, it's as if it got a tremendous boost in speed, enough to carry it onward to the next destination. The planet, of course, is so massive that this theft of momentum is utterly imperceptible. Flandreau's discovery sparked tremendous excitement at NASA and in the broader scientific community. Here was a chance to visit all the outer planets, worlds that had never been seen up close, in a mission that would take about 12 years, rather than the 30 or more it would take if each planet had to be visited separately. The proposal that emerged was called the Grand Tour. It was ambitious, perhaps overly so. The plan called for 4 spacecraft, 2 that would visit Jupiter, Saturn, and Pluto, and 2 others that would visit Jupiter, Uranus, and Neptune. But this was the early 1970s, and NASA's budget was being squeezed. The Apollo program was winding down, and attention was shifting to the space shuttle, which was consuming an ever larger share of available funding. The Grand Tour, with its projected cost of about $1 billion, became a political liability. In December of 1971, the program was canceled. Yet the dream didn't die. NASA engineers, unwilling to let this once-in-a-lifetime opportunity slip away, found a way to salvage the mission. They proposed a scaled-back version, just 2 spacecraft and a primary mission that would focus only on Jupiter and Saturn. But, crucially, the spacecraft would be designed with enough capability and fuel reserves that, if the first mission succeeded, one of them could continue onward to Uranus and Neptune. It was a compromise, but it kept the door open to achieving the Grand Tour's goals. The new mission was initially called Mariner Jupiter-Saturn, borrowing the name from NASA's successful Mariner program of planetary probes. The spacecraft would use technology proven on the earlier Mariner missions and on the Viking orbiters that had been sent to Mars. But as the design progressed, it became clear that these spacecraft were evolving into something new, something beyond the Mariner heritage. In March of 1977, just months before launch, NASA held a competition to rename the mission. The name Voyager was chosen, evoking the spirit of exploration and long journeys into the unknown. Each Voyager spacecraft was a marvel of 1970s engineering. Picture a box about the size of a compact car, mounted on a 10-sided structure that served as the main bus. Attached to this bus was a large dish antenna, 3.7 meters across, that would serve as the spacecraft's primary means of communicating with Earth. This antenna had to be kept pointed at Earth with extraordinary precision. From billions of miles away, Earth would appear as nothing more than a pale blue speck. And the spacecraft's radio beam was so narrow that being off by even a fraction of a degree would mean the signal would miss Earth entirely. The spacecraft carried an array of scientific instruments mounted on a scan platform that could be aimed independently of the main body. There were 2 cameras, one with a wide-angle lens and one with a narrow-angle lens for detailed close-ups. There were spectrometers for analyzing the composition of planetary atmospheres and surfaces by examining the light they emitted or reflected. There was a magnetometer for measuring magnetic fields, mounted at the end of a long boom to keep it away from the spacecraft's own magnetic interference. There were particle detectors for measuring charged particles in space. There were plasma wave detectors, cosmic ray detectors, and instruments for measuring plasma properties. Powering all of this was not solar panels. The outer solar system is far too distant from the Sun for solar power to be practical, but 3 radioisotope thermoelectric generators, or RTGs. These devices were essentially nuclear batteries. They contained pellets of plutonium-238, a radioactive isotope that produces heat as it decays. This heat was converted into electricity using thermocouples. At launch, the 3 RTGs together produced about 470 watts of electricity, enough to power several high-end desktop computers. But plutonium-238 has a half-life of 88 years, meaning that over time, the power output would gradually decline as the plutonium decayed. The mission planners knew this would eventually limit how long the spacecraft could operate, but they hoped for at least 5 years of useful data, long enough to complete the Jupiter and Saturn encounters. The computer systems aboard Voyager were, by modern standards, almost comically primitive. The spacecraft carried 3 different types of computers, 6 computers in total. The total memory available was about 68 kilobytes, less than a single email attachment might contain today. The processors operated at speeds measured in thousands of instructions per second, while a modern smartphone executes billions of instructions per second. Yet these computers would have to manage all the spacecraft's operations, control the instruments, store data, and handle the complex sequences needed to perform planetary flybys, all while operating autonomously for days or weeks at a time, since radio signals from Earth took hours to reach the spacecraft. Voyager 2 launched first on August 20th, 1977, atop a Titan 3E Centaur rocket. The launch was picture perfect, the rocket climbing into the blue Florida sky and arcing eastward over the Atlantic Ocean. 16 days later, on September 5th, Voyager 1 followed on an identical rocket. Though it launched second, Voyager 1 was placed on a faster, more direct trajectory. It would reach Jupiter 4 months before its twin and arrive at Saturn 9 months earlier. The reason for this launch order was strategic. Voyager 2's trajectory preserved the option to continue onward to Uranus and Neptune. But this came at the cost of a slower journey. Voyager 1, on the other hand, was aimed to make a close flyby of Saturn's largest moon, Titan, which scientists knew had a substantial atmosphere and was one of the most intriguing worlds in the solar system. But flying close to Titan would send Voyager 1 on a path that carried it up and out of the plane of the solar system, making any further planetary encounters impossible. The plan was simple. If the Voyager 1 successfully completed its Titan flyby and returned good data, then Voyager 2 would be cleared to skip Titan and continue to the outer planets. If Voyager 1 failed, Voyager 2 could be retargeted to visit Titan itself, sacrificing the grand tour but ensuring that this important moon was studied. Just 13 days after launch, Voyager 1 provided a preview of the wonders to come. From a distance of 7.25 million miles, still well within the inner solar system, it turned its cameras back toward home and captured the first-ever photograph showing the Earth and Moon together in a single frame. It was a humbling image, our world and its companion reduced to tiny crescents against the black void, a reminder of how small we are and how far these spacecraft would travel. The journey to Jupiter would take more than a year for Voyager 1, a bit longer for Voyager 2. During this phase, the spacecraft were not idle. Engineers put the instruments through their paces, checking and calibrating every system. The spacecraft practiced the complex sequences they would execute during the planetary encounters, aiming their instruments at distant stars and calibrating their cameras. And slowly, inexorably, the two Voyagers arced outward through the inner solar system, crossing the asteroid belt without incident. Space is vast and empty, and the chances of hitting anything were vanishingly small, and pressing on toward the realm of the giant planets, Jupiter, the first revelation. As Voyager 1 approached Jupiter in early 1979, anticipation at NASA and in the worldwide scientific community reached a fever pitch. Jupiter, the king of planets, was already known to be a world of extremes. Ground-based telescopes had shown its banded clouds, its great red spot, a storm large enough to swallow multiple Earths, and had revealed that it possessed at least 13 moons. Pioneer 10 and Pioneer 11 had flown past the planet in 1973 and 1974, returning the first close-up images and confirming that Jupiter's environment was even more hostile than expected, with intense radiation belts that had nearly crippled Pioneer 11's instruments. But Voyager would go further. Its instruments were more sophisticated, Its cameras had higher resolution, and the mission planners had learned from pioneers' experiences. Photography began in January of 1979, when Voyager 1 was still more than 50 million miles away. Even from that distance, the images being returned were already better than the best views from Earth-based telescopes. Scientists watched, mesmerized, as Jupiter grew in the camera's field of view, its details becoming sharper with each passing day. Voyager 1 made its closest approach to Jupiter on March 5, 1979, passing about 220,000 miles above the cloud tops, close enough that the spacecraft had to move quickly to avoid being captured by Jupiter's immense gravity. The encounter lasted only a few hours at closest approach, but Voyager 1 had been observing intensely for weeks beforehand and would continue for weeks afterward. In total, it captured almost 19,000 images of Jupiter and its moons. What those images revealed transformed our understanding of this giant world. The Great Red Spot, which had been a permanent feature of Jupiter for at least 300 years of telescopic observations, was revealed to be a colossal anticyclonic storm, spinning counterclockwise with winds of several 100 miles per hour at its edges. It was surrounded by smaller storms and eddies, some of which were pulled into the red spot's circulation like leaves caught in a whirlpool. The entire atmosphere was revealed to be in constant, turbulent motion, with jet streams racing around the planet at different latitudes and storms forming, merging, and dissipating in complex patterns. One of the most startling discoveries came from images of the night side of Jupiter. As Voyager looked back at the planet from beyond its orbit, with the Sun behind the planet, it detected faint rings. Jupiter, like Saturn, had a ring system. These rings were nothing like Saturn's brilliant icy bands. They were dark, composed of tiny dust particles, and so faint that they had never been detected from Earth. But they were there, extending out from Jupiter's cloud tops and held in place by the gravity of small inner moons. Yet the greatest revelations came from Jupiter's moons. Before Voyager, these moons had been little more than points of light, their sizes and orbits known, but their surfaces and properties largely mysterious. Voyager 1 trained its cameras on the four largest moons, Io, Europa, Ganymede, and Callisto, and what it saw was astonishing. Io, the innermost of the large moons, appeared on the first images as a yellow-orange world mottled with dark spots. Scientists initially thought these might be impact craters, but as more images came in and were studied, a navigation engineer named Linda Morabito noticed something strange in one image. There was a crescent-shaped feature on the limb of Io, rising up from the surface like a mushroom cloud. When the contrast was enhanced, it became clear what it was: an active volcanic plume, rising 250 miles above Io's surface. It was a discovery that sent shockwaves through the scientific community. Here was the first active volcano discovered beyond Earth, and as more images were analyzed, more volcanoes were found. Io turned out to be the most volcanically active world in the entire solar system, with lava flows and eruptions happening constantly across its surface. The heat driving this volcanism came not from radioactive decay in Io's interior, as drives Earth's volcanism, but from tidal heating. Jupiter's immense gravity stretches and squeezes Io as it orbits, and this constant kneading generates tremendous amounts of heat, enough to keep Io's interior molten and drive continuous eruptions. Europa, the next moon outward, was entirely different. Its surface was smooth, bright white, covered in water ice. But the ice was crisscrossed with a network of cracks and ridges, and there were very few impact craters, suggesting that the surface was young, constantly renewed by some process. Scientists began to hypothesize that beneath Europa's icy shell there might be a subsurface ocean of liquid water, kept from freezing by tidal heating similar to what powers Io's volcanoes. If such an ocean existed, it would be one of the most intriguing places in the solar system to search for life. This hypothesis would be strengthened by later missions, and today Europa is considered one of the prime targets for future exploration. Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, showed a surface divided into two types of terrain: dark, ancient, heavily cratered regions, and lighter, younger regions covered with complex patterns of grooves and ridges. It appeared that Ganymede had experienced geological activity in its past, with tectonic processes reshaping parts of its surface. Callisto, the outermost of the four large moons, was heavily cratered, its ancient surface a record of 4 billion years of impacts. 4 months after Voyager 1's encounter, Voyager 2 arrived at Jupiter. Its trajectory was slightly different, offering different viewing angles and the opportunity to observe changes in Jupiter's atmosphere over the intervening time. Voyager 2 confirmed that 8 of the 9 volcanoes spotted by Voyager 1 on Io were still active, suggesting that volcanic activity was not just constant, but ubiquitous on that tortured world. Together, the 2 Voyagers took more than 33,000 images of the Jupiter system and returned a wealth of data on its magnetic field, radiation environment, and plasma environment. The findings revolutionized planetary science. Before Voyager, the moons of the outer planets had been thought of as cold, dead worlds, geologically inert balls of ice and rock. Voyager showed that this was far from true. These moons were complex, diverse, geologically active worlds in their own right, each with its own story to tell. The implications were profound. If there could be active geology and potentially liquid water oceans in the frigid outer solar system, then the possibilities for where life might exist in the universe suddenly seemed much broader. Saturn and Titan, the jewel of the solar system. After their encounters with Jupiter, both Voyagers continued outward toward Saturn, the solar system's most visually stunning planet with its magnificent ring system. The journey from Jupiter to Saturn took about a year and a half, and during that time the spacecraft coasted through interplanetary space, their instruments monitoring the solar wind and cosmic rays, their cameras occasionally turning to observe distant targets. Voyager 1 arrived at Saturn in November of 1980. As it had at Jupiter, Voyager began intensive observations weeks before closest approach, watching as Saturn grew from a distant star to a magnificent world of subtle bands and swirls, orbited by its glittering rings. The encounter was designed not just to study Saturn itself, but to make a close flyby of Titan, Saturn's largest moon and the second largest moon in the solar system after Ganymede. Titan had long been known to possess an atmosphere, making it unique among moons. Spectroscopic observations from Earth had revealed the presence of methane in Titan's atmosphere, and there were hints that the atmosphere might be substantial, perhaps even denser than Earth's. But the true nature of Titan's atmosphere and surface remained mysterious, hidden beneath an opaque haze. Voyager 1's flyby of Titan on November 12, 1980, was one of the mission's highest priorities. The spacecraft passed just 4,000 miles from Titan's surface, closer than it would come to Saturn itself. As the images came in, scientists were both delighted and frustrated. Delighted because the data confirmed that Titan's atmosphere was indeed thick and substantial, composed primarily of nitrogen with a surface pressure 1.5 times that of Earth's. Frustrated because the thick orange haze in Titan's upper atmosphere completely obscured the surface. Voyager's cameras could not penetrate the haze, so while the spacecraft returned a wealth of data about Titan's atmosphere, the nature of its surface remained a mystery. The atmospheric data, however, was remarkable. Titan's atmosphere was revealed to be chemically complex, with methane, ethane, and various hydrocarbons present. The surface temperature was about -290 degrees Fahrenheit, cold enough that water ice would be as hard as rock, but right at the temperature where methane could exist as a liquid. Scientists began to speculate that Titan might have lakes, or even seas of liquid methane and ethane on its surface, making it in some ways analogous to Earth, with the methane cycle replacing Earth's water cycle. Methane rain falling from methane clouds, flowing in methane rivers to collect in methane seas. After passing Titan, Voyager 1 continued inward toward Saturn, making its closest approach to the planet on November 12th, passing 80,000 miles above the cloud tops. Saturn itself proved to be a more subtle world than Jupiter. Its atmospheric bands were less vivid, with pale yellows and creams dominating. But Voyager revealed fine structure in the clouds, smaller storms and eddies, and wind patterns that were in some ways even more extreme than Jupiter's, with equatorial winds reaching speeds of 1,000 miles per hour. The real glory of Saturn, however, was its rings. From Earth, even through large telescopes, Saturn's rings appear as fairly simple structures, a few broad bands separated by gaps. The largest gap, the Cassini division, had been known since the 17th century. But as Voyager 1's images poured in, scientists were stunned by the complexity revealed. The rings were not a few bands, but thousands upon thousands of individual ringlets, narrow bands of material each in its own distinct orbit. The rings showed waves, braids, spokes, dark radial features that seemed to rotate with the rings like the spokes of a wheel. Some rings seemed to be kept in place by the gravitational influence of small moons, shepherd moons that orbited just inside or outside a ring and prevented its material from spreading. Voyager 1 discovered several new moons of Saturn, small worlds that had been too faint to detect from Earth. Among these were Atlas, orbiting in a gap in the rings, and Prometheus and Pandora, shepherd moons that flanked the narrow F ring and kept it confined. The spacecraft also studied several of Saturn's known moons. Mimas, one of the mid-sized icy moons, was revealed to have a gigantic impact crater, fully 1/3 the diameter of the moon itself. The impact that created it must have come close to shattering Mimas completely. Enceladus, another icy moon, showed a surprisingly young-looking surface with few craters and strange grooved terrain, suggesting that it too might be geologically active. The Voyager 1 encounter with Saturn was deemed a complete success. Every one of its primary objectives had been met, and the data being returned exceeded all expectations. Now came the critical decision point. Voyager 1's trajectory, designed to provide the close Titan flyby, had sent it upward out of the plane of the solar system at a steep angle. It could not reach Uranus or Neptune. But Voyager 2, still on its way to Saturn, could. The trajectory was there, the option preserved. The spacecraft was healthy, functioning beautifully. NASA made the decision to extend Voyager 2's mission. After its Saturn encounter, it would continue to Uranus, and if it was still functioning, onward to Neptune. The grand tour would happen after all. Voyager 2 reached Saturn in August of 1981, 9 months after its twin. Its trajectory was different, designed now to set up the long journey to Uranus. It could not make a close Titan flyby. That was Voyager 1's job. But it was targeted to fly closer to Saturn itself and to approach from a different angle, providing complementary observations. Voyager 2 confirmed and extended the discoveries made by Voyager 1, capturing additional images of the rings, studying more moons, and providing new perspectives on Saturn's atmosphere. One of Voyager 2's contributions was a detailed study of Saturn's magnetic field and magnetosphere. Like Jupiter, Saturn possesses a powerful magnetic field generated by currents in its deep interior. This field creates a magnetosphere, a region around the planet where charged particles from the Sun are trapped and channeled by the magnetic field. Voyager 2 measured the shape and extent of this magnetosphere, tracked how it interacted with Saturn's moons, some of which orbit within it, and detected radio emissions generated by charged particles spiraling along magnetic field lines. After its Saturn encounter, Voyager 2 began the long coast toward Uranus, a journey that would take 4.5 years. Voyager 1, meanwhile, continued northward out of the solar system plane, its planetary exploration phase complete, but its mission far from over. Uranus and Neptune, into the unknown. The years between Saturn and Uranus were, in a sense, a test of endurance. Voyager 2 was now farther from Earth than any spacecraft had ever traveled, and it was heading into even more distant and unknown territory. The spacecraft itself was aging. It had been designed for a 5-year mission, Jupiter and Saturn, and had already exceeded that design life. Some systems had degraded or failed. The scan platform, the movable platform that held the cameras and other instruments, had temporarily seized up during the Saturn encounter, causing a nail-biting delay before engineers managed to free it. The team learned to be gentler with the platform, moving it more slowly, nursing it along. Communication was also becoming more challenging. The farther Voyager traveled, the weaker its radio signals became by the time they reached Earth. The Deep Space Network, NASA's system of giant radio antennas in California, Spain, and Australia, had to be continually upgraded to keep pace. Engineers developed new techniques for combining signals from multiple antennas, effectively creating larger virtual antennas. They reprogrammed Voyager 2's computers to compress data more efficiently, squeezing more information into each radio transmission. They even upgraded the software to use more sophisticated error correction codes, ensuring that data corrupted by noise during the billion-mile journey could be reconstructed. In November of 1985, Voyager 2 began its approach to Uranus. This was a world about which very little was known. Discovered in 1781, Uranus was the first planet found in modern times, doubling the known size of the solar system at a stroke. Ground-based observations had revealed that it was a gas giant, smaller than Jupiter or Saturn, but still massive by terrestrial standards, about 4 times the diameter of Earth, and containing about 15 times Earth's mass. Its atmosphere was known to contain hydrogen, helium, and methane, which gave the planet its blue-green color. It possessed at least 5 known moons, all named after characters from Shakespeare and Alexander Pope: Miranda, Ariel, Umbriel, Titania, and Oberon. The most unusual thing about Uranus was its rotation. Most planets spin roughly upright, their rotational axes nearly perpendicular to the plane of their orbits around the Sun. Uranus, by contrast, spins on its side, its rotational axis tilted 98 degrees from the vertical. This means that Uranus's poles alternately point almost directly at the Sun as the planet orbits, giving it the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. Voyager 2 made its closest approach to Uranus on January 24, 1986, passing within 50,000 miles of the cloud tops. The encounter took place while one of Uranus's poles was pointed nearly at the Sun, so Voyager's view was, in essence, looking down onto the planet's southern hemisphere as if looking at a target from above. The first impressions of Uranus were of a remarkably bland world. Its atmosphere showed almost no visible features, just a uniform pale cyan color. There were no dramatic storms like Jupiter's Great Red Spot, no cloud bands like Saturn's. The planet appeared almost featureless. Only when the images were heavily processed and enhanced did subtle details emerge. A few faint clouds, some slight banding, hints of structure. The atmosphere was clearly there, but its dynamics were muted compared to the other giant planets. Voyager did, however, reveal a complex and surprising magnetic field. Scientists had expected Uranus's magnetic field to be aligned roughly with its rotation axis, as is the case for Earth and the other planets with magnetic fields. Instead, Voyager found that Uranus's magnetic field was tilted 60 degrees from its rotation axis and offset from the center of the planet. This bizarre configuration meant that as Uranus rotates, its magnetic field wobbles and twists, creating an extremely complex magnetosphere that differs drastically from any other planets. The true treasures of the Uranus system turned out to be its moons. Voyager 2 discovered 10 previously unknown moons, small irregular worlds orbiting between the 5 large classical moons. The large moons themselves were revealed to be a diverse collection. Miranda, the smallest and innermost of the classical moons, turned out to be one of the strangest objects in the solar system. Its surface was a bizarre patchwork of different terrains, ancient, heavily cratered regions next to younger grooved and ridged areas, cliffs and canyons miles deep, features that looked as though they had been assembled at random. One theory is that Miranda was shattered by a massive impact and then reassembled, with pieces settling back together in a jumbled arrangement. Ariel showed signs of geological activity with smooth regions that appeared to be younger, possibly resurfaced by cryovolcanism, volcanoes that erupt ice rather than rock. Umbriel was dark and heavily cratered, ancient and unchanging. Titania and Oberon, the two largest, were also heavily cratered, but showed some signs of past geological activity. Voyager 2 also studied Uranus's rings, which had been discovered in 1977 when Uranus passed in front of a star, and the rings briefly blocked the star's light. These rings were revealed to be narrow and dark, composed of material so black that it reflects only a few % of the sunlight hitting it. 2 new rings were discovered by Voyager, bringing the total to 11. Unlike Saturn's broad, bright bands of icy particles, Uranus's rings are narrow ribbons of dark particles, possibly organic material or radiation-darkened ice, held in place by small shepherd moons. The Uranus encounter concluded in February of 1986, and Voyager 2 once again adjusted its course and headed outward, this time for Neptune. The journey would take 3.5 more years, carrying the spacecraft another billion miles into the outer darkness of the solar system. Neptune had been discovered in 1846, its existence predicted by mathematical calculations before it was seen, based on perturbations in Uranus's orbit. Like Uranus, it was a gas giant, but slightly smaller and denser. Ground-based observations suggested that Neptune might be more dynamic than Uranus, with possible atmospheric activity, but details were impossible to discern at such a distance. Voyager 2 began its approach to Neptune in June of 1989. As the planet grew in the spacecraft's cameras, it became clear that Neptune was indeed very different from Uranus. Its atmosphere was a deeper, richer blue, and it showed obvious structure. White clouds, dark ovals, bands of different shades. Here was a world that, despite being farther from the Sun and colder than Uranus, was clearly more active. The encounter took place on August 25, 1989. Voyager 2 came within 3,000 miles of Neptune's cloud tops, the closest approach to any body of its entire grand tour. The spacecraft revealed Neptune to be a world of surprises. A giant storm, called the Great Dark Spot, dominated the southern hemisphere, similar to Jupiter's Great Red Spot but smaller and apparently less permanent. High-altitude clouds streaked across the planet, composed of methane ice crystals, driven by the fastest winds in the solar system, reaching over 1,200 miles per hour. Neptune's magnetic field, like Uranus's, was tilted and offset from the planet's center, at an angle of 47 degrees to the rotation axis. This similarity suggested that something about the internal structure of these ice giant planets produces tilted magnetic fields, a phenomenon still not fully understood. Voyager discovered 6 new moons of Neptune, small, irregular worlds in addition to the 2 large moons already known, Triton and Nereid. Triton, Neptune's largest moon, was one of the primary targets of the encounter, and Voyager passed just 25,000 miles from its surface. Triton turned out to be one of the most remarkable worlds in the solar system. It is the coldest known surface in the solar system, with temperatures around minus 391 degrees Fahrenheit. Despite this extreme cold, Triton proved to be geologically active. Voyager's cameras captured dark plumes rising from the surface, nitrogen geysers erupting through the icy crust and carrying dark material up into the thin atmosphere before the winds carried it downrange, creating dark streaks across the frozen landscape. Triton's surface was young, with very few impact craters, indicating that geological processes had resurfaced it relatively recently. The terrain was a mixture of different features: smooth plains, cantaloupe-like pitted regions, ridges, and valleys. Some regions appeared to be frozen nitrogen lakes. The surface composition included nitrogen ice, methane ice, carbon dioxide ice, and water ice, a mixture that would be exotic and alien by Earth standards, but which becomes possible in the extreme cold at Neptune's distance from the Sun. Triton is also unusual in that it orbits Neptune in a retrograde direction, backward compared to Neptune's rotation and to the orbits of most other moons. This is strong evidence that Triton did not form alongside Neptune but was captured from elsewhere, perhaps from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. The capture process would have been violent, with tidal forces heating Triton's interior, potentially explaining its geological activity. Over time, tidal forces have circularized Triton's orbit, but they are also slowly drawing it closer to Neptune. In about 3.5 billion years, Triton will pass within Neptune's Roche limit, the distance at which tidal forces will overcome the Moon's own gravity, and it will be torn apart, its material forming a magnificent new ring system around Neptune. Just before Voyager 2 left the Neptune system, it turned its cameras back toward the inner solar system. On February 14, 1990, at a distance of 3.7 billion miles from the Sun, Voyager 1 executed a command sequence that had been uploaded weeks earlier. Its cameras, which had been powered down since the Saturn encounter to conserve electricity, and because there were no more planets to photograph, were turned back on one last time. Voyager 1 rotated, sweeping its camera across the solar system, capturing 60 frames that would be assembled into a family portrait of the planets. The resulting images were dim and grainy. At such a distance, even giant Jupiter appeared as little more than a bright pixel. But one image in particular captured the imagination of the world. In a shaft of scattered sunlight, surrounded by the emptiness of space, was Earth, appearing as a tiny pale blue dot, just 0.12 pixels in size. Carl Sagan, who had been one of the original advocates for including cameras on Voyager, and who had pushed for this final imaging sequence, reflected on this image in words that have become iconic. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, on a mote of dust suspended in a sunbeam. This pale blue dot photograph became one of the most important images in the history of space exploration, a cosmic perspective on humanity's place in the universe. The Golden Record, a message in a bottle. Mounted on the exterior of each Voyager spacecraft is a golden record, a 12-inch gold-plated copper disc that contains sounds and images from Earth. This record is one of the most poignant aspects of the Voyager mission, a message intended not for human eyes or ears, but for any extraterrestrial intelligence that might, in the distant future, encounter one of the spacecraft drifting through interstellar space. The idea for the record came from Carl Sagan and his colleagues at Cornell University. NASA had already included plaques on the Pioneer 10 and 11 spacecraft, simple engravings showing the form of a man and woman, the spacecraft's trajectory, and a symbolic representation of Earth's location. But for Voyager, Sagan proposed something more ambitious, a record that would carry sounds and images, capturing something of Earth's diversity and the nature of the civilization that had built the spacecraft. NASA approved the concept, but provided almost no funding, so the record was created largely through volunteer effort. Sagan assembled a small team, including his colleague Frank Drake, science journalist Timothy Ferris, artist John Lomberg, and writer Anne Druyan. They had less than a year to conceive, select, and produce the record's contents. It was an impossible task. How do you represent an entire planet, an entire species, in 2 hours of audio and 116 images? The record contains greetings in 55 languages, from ancient Akkadian to modern Chinese, each speaker offering a brief message of peace and goodwill. There are the sounds of Earth, thunder and rain, wind and waves, bird calls and whale songs. There are the sounds of human activity, a heartbeat, footsteps, laughter, a kiss, a baby crying. There are the sounds of human technology, trains, cars, aircraft, even a Saturn V rocket launching, the same type of rocket that carried humans to the moon. There is music, 90 minutes of it, selected to represent the diversity of human musical expression across cultures and time. The selection includes Bach's Brandenburg Concerto No. 2, representing Western classical music. There is Chuck Berry's Johnny B. Good, representing rock and roll. There are traditional songs from around the world, a Navajo night chant, a Japanese bamboo flute piece, Peruvian panpipes, a Georgian chorus, Indonesian gamelan music, and more. There is a Beethoven string quartet, Mozart, Stravinsky, and Louis Armstrong. The images, 116 of them, were encoded as analog signals on the record. They show mathematical and physical concepts, the structure of DNA, human anatomy, images of plants and animals, landscapes and seascapes, cities and farms, various human activities, and portraits of people from different cultures. The selection tried to be inclusive, showing humanity in its diversity, though constrained by the limits of what could fit and the technology available for encoding images onto an audio record. One of the most remarkable stories connected to the Golden Record involves Anne Druyan. On a June day in 1977, just weeks before Voyager's launch, Druyan went to Bellevue Hospital in New York to record her brain waves and other physiological data for the record. The idea was to include a representation of human thought and emotion in a form that an advanced civilization might be able to decode. As Druyan sat wired to the equipment, she was asked to think about various subjects: Earth's history, the problems facing humanity, her own life. What the team didn't know at the time, what wasn't revealed until years later, was that Druyan had just become engaged to Carl Sagan the night before. As she sat in that hospital room, her thoughts were suffused with love and hope for the future, emotions that were being recorded as electrical patterns in her brain. So, in a very real sense, the Golden Record carries not just sounds and images, but a record of human love, encoded in the electrical patterns of one woman's mind in a moment of joy. The record also includes a message from President Jimmy Carter, dated June 16, 1977. This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe. The record's cover is designed to be a sort of instruction manual. Engraved on it are diagrams showing how to play the record, what speed to use, how to decode the images. There is a map showing Earth's location relative to 14 pulsars, rapidly spinning neutron stars that emit radio pulses at precise intervals. Any advanced civilization capable of finding and retrieving Voyager would presumably be able to recognize these pulsar signatures and use them to determine where and when the spacecraft came from. In the center of the cover is a small sample of ultra-pure uranium-238, included as a sort of radioactive clock. Uranium-238 decays to lead at a known rate, with a half-life of 4.5 billion years. By measuring the ratio of uranium to lead in the sample, an alien civilization could determine how much time has passed since the record was assembled, allowing them to date it to within a few million years, even billions of years in the future. Of course, the chances that Voyager will ever be found by an extraterrestrial intelligence are vanishingly small. Space is vast beyond comprehension, and the spacecraft are tiny, moving slowly by cosmic standards. They could drift through the galaxy for billions of years without ever coming close to another star system, let alone one that harbors intelligent life. Carl Sagan himself acknowledged this, noting that the record was perhaps as much a message to ourselves as to any hypothetical aliens, a statement about who we are and what we value, frozen in time and sent into the cosmos. Yet there is something deeply moving about the Golden Record. It represents humanity at perhaps its best, reaching out in a spirit of openness and hope, trying to communicate across the ultimate barrier of space and time, creating something beautiful not for practical purposes, but because it speaks to something fundamental in the human spirit, the desire to be known, to be remembered, to say we were here, crossing the Heliopause, into interstellar space. After the encounter with Neptune in August of 1989, both Voyager spacecraft had completed their primary missions. They had visited all 4 giant planets, returned hundreds of thousands of images, and revolutionized our understanding of the outer solar system. But their journey was far from over. In fact, in many ways, the most remarkable phase of their mission was just beginning. Both Voyagers continued outward, coasting on the momentum gained from their final planetary encounters. They were now heading into a region of space that no human-made object had ever reached. The boundary between the realm dominated by the Sun and the realm of interstellar space. This boundary is called the Heliopause, and reaching it would be another historic milestone. To understand the Heliopause, we need to understand the heliosphere. The Sun doesn't just emit light and heat. It also constantly streams out a flow of charged particles, mostly protons and electrons, called the solar wind. This wind races outward in all directions at speeds of several hundred miles per second, carrying with it the Sun's magnetic field. The solar wind creates a bubble around the Sun, a region of space where the Sun's influence dominates. This bubble is the heliosphere, but the Sun is not alone in space. The galaxy itself is filled with a thin gas, the interstellar medium, consisting mostly of hydrogen and helium atoms. This interstellar medium has its own pressure, its own magnetic fields. As the solar wind pushes outward, it eventually encounters the interstellar medium pushing back. Somewhere far beyond the orbits of the planets, the two meet, and that meeting place is the Heliopause. Before Voyager, scientists had theoretical models of where the Heliopause should be, but no direct measurements. Estimates suggested it might be somewhere between 8 and 14 billion miles from the Sun, roughly 100 times the distance from the Sun to Earth. But there was uncertainty about its exact location and structure, and about what crossing it would actually mean in terms of the environment spacecraft would encounter. The journey to the Heliopause would take decades. The Voyagers were traveling fast by human standards. Voyager 1 at about 38,000 miles per hour relative to the Sun. Voyager 2 at about 35,000 miles per hour. But space is vast, and even at these speeds, the spacecraft inch outward at what seems an agonizingly slow pace when measured in astronomical units. Through the 1990s and 2000s, the Voyagers continued transmitting data. Most of their instruments had been shut down to conserve power, but a few key instruments remained active, measuring particles and magnetic fields in the outer reaches of the solar system. The spacecraft were exploring a region called the heliosheath, the outer layer of the heliosphere, where the solar wind has been slowed and deflected by its collision with the interstellar medium. In December of 2004, Voyager 1 crossed the termination shock, the boundary where the solar wind slows from supersonic to subsonic speeds as it begins to pile up against the pressure of the interstellar medium. This was the first spacecraft to reach this boundary, and it provided the first direct measurements of the termination shock's location and properties. Voyager 2 crossed the termination shock in August of 2007 at a different location, and revealing that the heliosphere is not perfectly spherical but somewhat squashed, influenced by the direction from which the interstellar medium is flowing past the solar system. For several years, both spacecraft traveled through the heliosheath, that strange transitional zone between the solar wind and interstellar space. It was a region of turbulence and complexity, where the slowed solar wind mixed and churned. Then, in August of 2012, Voyager 1's instruments detected an abrupt change. The flux of solar wind particles suddenly dropped to nearly zero, while the flux of higher-energy cosmic rays from interstellar space increased sharply. At the same time, measurements of the plasma environment showed that Voyager 1 was now surrounded by a much denser plasma than it had been, consistent with the properties of the interstellar medium. It took several months of analysis to confirm what had happened. On August 25, 2012, Voyager 1 had crossed the Heliopause. It had left the heliosphere and entered interstellar space. For the first time in history, a human-made object was traveling through the space between stars. The announcement, made by NASA in September of 2013 after careful verification, was momentous. Voyager 1 was now in a realm no spacecraft had ever reached, and it was sending back data about what interstellar space was actually like. The measurements revealed a denser plasma than in the outer heliosphere, with a different magnetic field orientation. The cosmic ray flux was higher, no longer partially shielded by the Sun's magnetic field. Voyager 1 was detecting particles that had been accelerated by supernova explosions in distant parts of the galaxy, particles that had traveled for millions or billions of years before washing over the spacecraft. One surprising finding was that the magnetic field direction didn't change when Voyager 1 crossed the heliopause. Scientists had expected that inside the heliosphere, the magnetic field would be dominated by the Sun's field, while in interstellar space it would align with the galactic magnetic field. But the field direction remained roughly constant across the boundary. This suggested that the Sun's influence on the local magnetic field extends even beyond the heliopause, or that the interstellar magnetic field in the Sun's immediate neighborhood happens to be aligned with the solar magnetic field. Voyager 2 followed its twin into interstellar space 6 years later, in November of 2018. It crossed the heliopause at a different location, about 11 billion miles from the Sun, compared to Voyager 1's crossing point at about 12 billion miles. This difference helped confirm that the heliosphere is not perfectly symmetrical. Voyager 2's crossing provided complementary data, and because Voyager 2 still had a functioning plasma science instrument, Voyager 1's had failed years earlier. It was able to make direct measurements of the plasma properties across the heliopause boundary. The data from both spacecraft revealed that the heliopause is not a static boundary but a dynamic, rippling surface, constantly moving in and out as the pressure from the solar wind fluctuates, and as the spacecraft move through regions where the interstellar medium has different densities. At times, Voyager 1 detected changes suggesting it had temporarily moved back into the heliosheath before definitively entering interstellar space. Both Voyagers continue to return data from interstellar space, measurements that are providing the first direct observations of this environment. They are measuring the density and temperature of the interstellar plasma, the strength and direction of magnetic fields, the flux of cosmic rays, and occasional bursts of plasma waves. These observations are helping refine our understanding of the structure of the heliosphere and the nature of the local interstellar medium. The fact that both Voyagers are still functioning, more than 47 years after launch, is a testament to the quality of their engineering and the skill of the team that operates them. But time is taking its toll. The engineering marvel. Keeping Voyager alive. The radioisotope thermoelectric generators that power the Voyager spacecraft are slowly dying. This is not a malfunction, but an inevitable consequence of physics. Plutonium-238 decays at a known rate, with a half-life of 87.7 years. Every year that passes, the RTGs produce slightly less power. At launch, in 1977, the 3 RTGs on each spacecraft together produced about 470 watts of electricity. By the year 2000, 23 years after launch, this had declined to about 392 watts. By 2022, 45 years after launch, power output had dropped to around 220 watts, less than half the original capacity. This decline has forced NASA's mission planners to make difficult choices. To keep the spacecraft operating, they have systematically shut down systems that are no longer essential. Heaters that once kept instruments warm in the cold of deep space have been turned off. The spacecraft themselves are now much colder than they were designed to operate, but remarkably, most systems continue to function. Cameras were powered down completely in 1990, after Voyager 1 captured the Solar System family portrait. The software that controlled the cameras was actually removed from the spacecraft's computers to free up precious memory for other tasks. One by one, scientific instruments have been shut down as power has become scarce. The ultraviolet spectrometer, the infrared spectrometer, the photopolarimeter, all have been turned off. As of 2026, only a handful of instruments remain active on each spacecraft. The magnetometer, measuring magnetic fields in interstellar space. The cosmic ray detector. The plasma science instrument on Voyager 2, which measures the density and temperature of charged particles. And the plasma wave instrument, which detects oscillations in the plasma. These 4 remaining instruments are returning irreplaceable data about the environment beyond the solar system, data that no other spacecraft can provide. The mission engineers have become masters at extracting every last bit of useful life from these aging spacecraft. In 2023, they implemented a clever power-saving measure. Each Voyager has a voltage regulator that triggers a backup power circuit if the spacecraft's voltage fluctuates too much. This backup circuit has access to a small reserve of power set aside for emergencies. The engineers realized they could tap into this reserve, using it to keep instruments running instead of holding it in reserve. It's a calculated risk. If there's a sudden voltage fluctuation, it could damage the instruments. But, after more than 45 years in space, the spacecraft's electrical systems have proven remarkably stable. The risk was deemed acceptable if it meant extending the mission's scientific return. NASA projects that the Voyagers might be able to keep at least one science instrument operating until approximately 2025 to 2028. Though this estimate keeps being revised as the engineers find new ways to extend the mission. After that, there may still be enough power to operate the spacecraft's radio transmitter and basic systems, allowing the spacecraft to send back engineering data. information about their own health and status, until perhaps 2036 or beyond. Eventually, though, power will drop below the minimum needed to operate the radio transmitter, and the Voyagers will go silent. They will continue their journey through space, but humanity will no longer be able to hear from them. The computer systems aboard a Voyager are, by modern standards, astonishingly primitive. The 3 computers on each spacecraft, the command and control system, the flight data subsystem, and the attitude and articulation control subsystem, together have about 68 kilobytes of memory. To put that in perspective, a typical smartphone photo file is larger than the total memory available to all 3 Voyager computers combined. The processors operate at speeds measured in thousands of instructions per second, while a modern smartphone executes billions of instructions per second. Yet these antiquated computers have performed flawlessly for nearly half a century, operating continuously in the harsh environment of space, subjected to temperature extremes, radiation, and the unforgiving vacuum. The very simplicity of the technology has, paradoxically, been an advantage. The larger transistors used in 1970s era chips are less susceptible to damage from cosmic radiation than the tiny transistors in modern processors. The limited memory space makes it easier to understand and troubleshoot problems. And, critically, the spacecraft's computers are reprogrammable. Engineers can upload new software to modify how the spacecraft operates, a capability that was cutting edge in 1977 and has proven invaluable as the mission has evolved far beyond its original design. This reprogrammability was put to the test in a dramatic way in late 2023 and early 2024, when Voyager 1 encountered one of its most serious problems in decades. In November of 2023, the spacecraft stopped sending back coherent data. Instead of the normal stream of science and engineering telemetry, it began transmitting what appeared to be gibberish, a repeating pattern of ones and zeros that made no sense. The problem was clearly in the flight data subsystem, the computer responsible for packaging data for transmission to Earth. For 5 months, a small team of engineers at the Jet Propulsion Laboratory worked to diagnose and fix the problem. The debugging process was excruciatingly slow. Every command sent to Voyager 1 takes about 22.5 hours to reach the spacecraft. The spacecraft's response takes another 22.5 hours to return to Earth. This means a simple command and response cycle takes 45 hours, nearly 2 days. If you send a command that doesn't work, or if you need to analyze the response and formulate a new command, you've just added another 2-day cycle to your troubleshooting process. In March of 2024, the team sent a special command called a poke to Voyager 1, instructing the flight data subsystem to execute different software sequences. 2 days later, they received a response that was different from the usual gibberish. An engineer at the Deep Space Network recognized the pattern and was able to decode it. It was a complete dump of the computer's memory, including all its software code and variables. Analyzing this memory dump, the engineers discovered the culprit. About 3% of the flight data subsystem's memory was corrupted. A single memory chip, containing critical portions of the computer's software, had failed. The cause of the chip's failure is uncertain. It might simply be wear and tear. After 46 years of continuous operation, components eventually fail. Or it might have been struck by an energetic particle from space, a cosmic ray that slammed into the chip with enough energy to damage its circuitry. Either way, the chip was dead, and there was no way to repair it. The solution required ingenuity. The corrupted chip contained code that was essential for the spacecraft's operation, code that had to be moved elsewhere in the computer's memory. But there was no single location in the remaining memory large enough to hold all the affected code. The team would have to divide the code into sections, store each section in a different available location, and then modify the code so that it would still function correctly despite being fragmented. They would also need to update all the references to this code throughout the rest of the computer's memory. On April 18, 2024, the team uplinked a modified version of the code responsible for packaging engineering data, relocated to new addresses in the computer's memory. They waited anxiously for the response. On April 20th, confirmation arrived. The modification had worked. For the first time in 5 months, Voyager 1 was sending back readable engineering data. The team celebrated, but their work wasn't done. Over the following weeks, they relocated the rest of the affected code, section by section, until finally Voyager 1 was fully operational again, returning both engineering and scientific data. It was a triumph of engineering skill and perseverance, fixing a computer chip from 15 billion miles away with technology nearly half a century old. The incident also served as a reminder of how fragile these aging spacecraft are, and how dedicated the small team that maintains them has become. Only about a dozen people now work on the Voyager mission, down from hundreds during the planetary encounters. Many of these engineers have been with the mission for decades. They have become specialists in maintaining systems that no longer exist anywhere else, using techniques and knowledge that are in danger of being lost as the engineers themselves age and retire. Communication with Voyager poses its own challenges. The spacecraft transmit data at a rate of only 160 bits per second, agonizingly slow by modern standards. A single high-resolution image from a smartphone would take hours to transmit at that rate, if Voyager's radios had the bandwidth to handle it at all. But this slow data rate is a consequence of distance and power. Voyager's transmitters output about 23 watts of power, roughly the same as a refrigerator light bulb. By the time this faint signal reaches Earth from billions of miles away, it has spread out over a vast area and weakened to an almost unimaginably faint whisper. The Deep Space Network antennas that receive Voyager's signals are engineering marvels in their own right. The largest antennas are 70 meters in diameter, massive dishes that can detect signals a billion times weaker than the power of a digital watch battery. Even with these enormous antennas and the most sensitive receivers available, the signal from Voyager is barely detectable. Engineers have continually upgraded the Deep Space Network over the decades to keep pace with the weakening signal as the spacecraft move farther away. The Voyager mission has also developed techniques to combine signals from multiple antennas, creating a larger, effective antenna. During critical events, antennas in different parts of the world are pointed at Voyager simultaneously, and their signals are combined in a process called arraying. This can effectively increase the sensitivity, allowing the detection of even weaker signals or the reception of data at higher rates. Recently, the Deep Space Network has faced its own challenges. Deep Space Station 43 in Canberra, Australia, the only antenna in the southern hemisphere capable of sending commands to Voyager, was offline for major upgrades throughout much of 2025. During this time, only limited communication with the Voyagers was possible, restricted to specific windows when other antennas could make contact. This added another layer of complexity and risk to managing these distant, aging spacecraft. The thrusters that control Voyager's attitude, its orientation in space, have also shown signs of age. The spacecraft must keep their high-gain antennas pointed precisely at Earth, despite traveling at thousands of miles per hour through the vast emptiness of interstellar space. This pointing is maintained by small thrusters that fire periodically to adjust the spacecraft's orientation. But the fuel lines for these thrusters have been clogging over time, as residue builds up inside them, reducing the thruster's effectiveness. In 2017, engineers performed a remarkable operation on Voyager 1. The spacecraft had been using a set of attitude control thrusters to maintain its orientation, but these thrusters were showing signs of clogging. The engineers decided to switch to a different set of thrusters called trajectory correction maneuver thrusters that hadn't been fired since 1980 during the Saturn encounter. It was uncertain whether these thrusters would still work after sitting dormant for 37 years. The command was sent, and 2 days later the response came back. The thrusters had fired perfectly. The switch extended Voyager 1's operational life by several years. The same operation was successfully performed on Voyager 2, and in 2024, both spacecraft underwent additional thruster swaps as the clogging problem persisted. The spacecraft are now, in the words of Voyager project manager Suzanne Dodd, operating with everything single string, meaning there are no longer any backup systems. If a critical component fails, there may be no way to work around it. Every day that Voyager continues to function is, in a sense, borrowed time, a gift from the foresight of the engineers who designed these spacecraft to be robust, and the skill of those who continue to maintain them. The lonely voyage ahead. As of January 2026, Voyager 1 is approximately 15.4 billion miles from Earth, in the constellation Ophiuchus. It is traveling outward at about 38,000 miles per hour relative to the Sun, or roughly 3.6 astronomical units per year. An astronomical unit is the average distance from Earth to the Sun, about 93 million miles. Every year, Voyager 1 moves about 3.6 times farther from the Sun than Earth's entire orbit is wide. Voyager 2 is about 12.8 billion miles away in the constellation Telescopium. It's traveling at about 35,000 miles per hour, adding roughly 3.3 astronomical units to its distance from the Sun each year. Both spacecraft have long since left the realm where the Sun's influence is dominant and entered the space between stars, the interstellar medium. But don't be fooled by the term interstellar. While Voyagers have indeed entered interstellar, space in one sense, they're beyond the Sun's heliosphere and surrounded by the plasma and magnetic fields of the galaxy rather than those of the Sun. They're still, in another sense, very much within the solar system's gravitational domain. The Sun's gravity extends much, much farther than the heliosphere. The solar system is not finished at the Heliopause. It extends outward in a vast sphere, encompassing regions that Voyager won't reach for thousands, even tens of thousands of years. Beyond the orbits of the known planets lies the Kuiper Belt, a region populated by countless icy bodies, including Pluto and similar dwarf planets. The Kuiper Belt extends from about 30 astronomical units from the Sun, just beyond Neptune, out to perhaps 50 or 60 astronomical units. Voyager 1 passed through the Kuiper Belt's orbital zone decades ago. Though the belt is so vast and its objects so widely dispersed, that the chances of Voyager coming close to any Kuiper Belt object were, and remain, vanishingly small. Far beyond the Kuiper Belt, at distances of perhaps several thousand to more than 100,000 astronomical units from the Sun, lies the hypothesized Oort cloud. This is a spherical shell of icy bodies, the remnants of the solar system's formation loosely bound to the Sun by its gravity. The Oort cloud is thought to contain trillions of comets. When gravitational perturbations occasionally send one of these comets falling toward the inner solar system, we see it as a long-period comet, taking centuries or millennia to complete its orbit. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of comets and from theoretical models of how the solar system formed. But if it exists as theorized, it is truly immense, and Voyager is only now beginning the journey through it. At its current speed, Voyager 1 will not fully exit the Oort cloud for another 30,000 years. Let that sink in for a moment. 30,000 years. When Voyager 1 finally leaves the Oort cloud, humans might not even exist anymore, at least not in a form we would recognize. Civilizations will have risen and fallen. Languages, cultures, entire ways of life will have come and gone. The Voyager spacecraft will outlive not only their creators, but potentially the entire legacy of their civilization. After leaving the Oort cloud, Voyager 1 will continue drifting through space, gradually passing near other stars. In about 40,272 years, Voyager 1 will pass within 1.7 light-years of the star Gliese 445, also known as AC, plus 793888, a small red dwarf in the constellation Camelopardalis. 1.7 light-years is still an enormous distance, more than 100,000 times the distance from Earth to the Sun. But by interstellar standards, it's a close encounter. Gliese 445 will be closer to Voyager 1 at that point than any other star is to us now. Voyager 2's trajectory will carry it to a different region of the galaxy. In about 40,000 years, it will pass within 1.7 light-years of Ross 248, another red dwarf, in the constellation Andromeda. Then, in 296,000 years, it will pass within 4.3 light-years of Sirius, the brightest star in Earth's night sky. These are the first close encounters, but the journey continues essentially forever. The Voyagers will spend millions, even billions of years drifting through the galaxy. Every few 100,000 years, they will pass relatively near another star system. Most of these encounters will be distant, with the spacecraft passing many light-years away. But occasionally, by chance, Voyager might pass closer, perhaps even through another star's equivalent of the Oort cloud. What will the galaxy be like in a billion years when Voyager is still traveling? Stars that exist now will have burned out. New stars will have formed from collapsing clouds of gas and dust. The Sun will have evolved into a red giant, swelling up to engulf the inner planets, then shedding its outer layers to become a white dwarf. Earth, if it survives the Sun's red giant phase at all, will be a scorched, lifeless cinder, or perhaps consumed entirely. But Voyager will still be out there, sailing silently through the void. The spacecraft themselves will change over these vast timescales. Even in the hard vacuum of space, there are occasional collisions with atoms and dust grains. Over millions of years, these impacts will gradually erode the spacecraft's surfaces. The golden records, those messages from Earth, will become pitted and scratched. The spacecraft's exteriors will be darkened by micrometeorite impacts and cosmic radiation, but the rate of decay will be extraordinarily slow. Space is vast and empty. In the Milky Way galaxy, the average distance between atoms in interstellar space is a few atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 25 billion molecules per cubic centimeter. Space is emptier than the best vacuum we can create in laboratories by more than 15 orders of magnitude. In such emptiness, collisions are rare, and the spacecraft will erode at a glacial pace. Eventually, after billions of years, Voyager will have traveled a significant fraction of the way across the galaxy. The Milky Way is about 100,000 light-years in diameter, and at its current speed, Voyager is moving at about 1/10,000th the speed of light. This means it would take about 1 billion years to traverse 100 light-years and 10 billion years to cross the galaxy, longer than the current age of the universe. But the galaxy itself is moving, rotating around its center, and Voyager is moving with it. So the notion of crossing the galaxy is somewhat meaningless. Voyager will simply continue to orbit the galactic center along with the Sun and all the other stars, slowly passing close to some stars and drifting away from others in an eternal, random walk through the stellar neighborhood. Barring a direct collision with something solid, an event of such low probability that it's unlikely to happen even over billions of years, Voyager will essentially last forever. Or at least, it will last until the far future when the universe itself undergoes profound changes. In trillions of years, star formation will cease as the galaxy runs out of gas. The stars that exist will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. The universe will enter what cosmologists call the degenerate era, dominated by these stellar remnants. Voyager will still be there, an artifact from a time when stars still shone and planets still harbored life. In the unimaginably distant future, in 10 to the 32nd to 10 to the 40th power years, even protons may decay, if certain theories of physics are correct. When that happens, the atoms that make up Voyager will gradually disintegrate. The spacecraft will cease to be a coherent object and will dissolve into a cloud of exotic particles and radiation. But until then, Voyager remains, a wanderer, a testament to a species that once looked up at the stars and dared to reach beyond their world. What happens if, against all odds, Voyager is one day found by an extraterrestrial intelligence? The Golden Record provides instructions for how to play it and how to decode its contents. The beings who find it, if they exist and if they are technologically advanced enough to retrieve the spacecraft, would presumably be able to figure out the record's contents. They would hear the sounds of Earth, our music, our languages, the wind and rain, and the calls of animals that lived on a world they will likely never see. They would see our images, the structure of DNA, the form of the human body, pictures of our cities and landscapes. They would know that we existed, that we were curious, that we reached out into the cosmos in an attempt to communicate, even knowing that any response would be impossibly delayed. They would know, in Carl Sagan's words, that we tried to survive our time so we may live into theirs. Of course, the reality is that Voyager will almost certainly never be found. Space is too vast, and the spacecraft too small. The chance of an encounter is infinitesimally low. But that's not really the point. The Golden Record, like the mission itself, is about more than practical outcomes. It's about what these artifacts say about humanity, that we are a species capable of looking beyond ourselves, of creating something not for immediate gain, but for the sheer sake of reaching out into the unknown. In that sense, Voyager's message has already been received. We received it ourselves in the act of sending it, the legacy and meaning of Voyager. Nearly half a century after their launch, the Voyager spacecraft have given us gifts that extend far beyond the stunning images of planets and moons they returned. They have fundamentally changed our understanding of the solar system and our place within it. Before Voyager, the outer planets were mysterious worlds known only as points of light or blurry disks through telescopes. Voyager transformed them into real places, each with its own distinct character and story. Jupiter became a world of storms and radiation, orbited by moons that were themselves fascinating worlds. Saturn's rings were revealed to be structures of exquisite complexity. Uranus and Neptune, those distant ice giants, each had their own surprises. And the moons, oh, the moons, turned out to be far more interesting than anyone had imagined. Volcanic Io, icy Europa with its possible subsurface ocean, nitrogen geysering Triton, these became places we could imagine exploring in more detail, targets for future missions. Voyager also taught us about the nature of discovery itself. The mission demonstrated that sometimes the most important findings are the ones you don't expect. Linda Morabito discovering volcanic plumes on Io, the unexpected complexity of Saturn's rings, the bizarre tilted magnetic fields of Uranus and Neptune. These were not predictions verified, but genuine surprises that forced scientists to rethink their understanding. Voyager showed that nature is often stranger and more wonderful than we imagine, and that the act of exploration, of going to look for yourself rather than simply theorizing from a distance, reveals truths that no amount of speculation could have predicted. The pale blue dot photograph, taken as Voyager 1 looked back at the inner solar system from 4 billion miles away, has become one of the most iconic and meaningful images ever captured. Carl Sagan's reflection on this image has been quoted countless times, but it bears repeating, at least in part, because it captures something essential about Voyager's legacy. Consider again that dot, Sagan wrote. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That perspective, that cosmic sense of scale and our tiny place within it, is perhaps Voyager's most important contribution. It's a perspective that should engender humility, a reminder that our planet is fragile and precious, the only home we have in an incomprehensibly vast universe. The Voyager mission also represents a kind of human achievement that seems increasingly rare. It was ambitious, risky, and undertaken without any guarantee of success or immediate practical benefit. There was no economic return on sending robots to the outer planets. There was no military advantage. It was done for knowledge, for curiosity, for the sheer human desire to explore and understand. In that sense, Voyager represents humanity at its best, looking outward, asking questions, reaching beyond ourselves. The engineers and scientists who built and operated Voyager had to be optimistic. They had to believe that solving complex problems was possible, that careful design and rigorous testing would pay off, that ingenuity could overcome obstacles, and they had to be patient. The journey to Neptune alone took 12 years. The mission has now lasted 47 years. Far longer than the original 5-year design life. The people who launched Voyager in their 20s and 30s are now in their 70s and 80s, or have passed away. The mission has spanned careers, lifetimes even, yet it continues. There's something profoundly moving about that continuity. A small team of dedicated engineers and scientists, many of whom have been with the mission for decades, continues to monitor these aging spacecraft, solving problems, extending the mission year by year. They do this knowing that Voyager's end is inevitable and not far off now. Perhaps another few years, maybe a decade if they're lucky, and then the power will finally fail, and Voyager will go silent. But they persist, extracting every last bit of scientific return, honoring the legacy of those who came before them and the spacecraft that have performed so remarkably. When Voyager does finally go silent, it will mark the end of an era. No human-made object will have traveled as far as Voyager won for decades, perhaps generations. The next truly interstellar missions are only in the planning stages, and it will be many years before they launch, and additional decades before they reach the distances Voyager has achieved. For a long time, Voyager will remain humanity's most distant emissary. But even after we can no longer communicate with it, Voyager's journey will continue. The spacecraft will carry the golden record, that message from Earth, into the far future. Whether anyone ever finds it is almost beside the point. The act of sending it, of trying to communicate across the ultimate barrier of time and space, says something important about who we are. It says that we are a species that creates, that wonders, that hopes. It says that we believe, or want to believe, that we are part of something larger than ourselves, that there might be other minds out there in the cosmos, and that communication, understanding, connection across the void is worth striving for. Carl Sagan once said that the Voyager record is more a gift to ourselves than to any extraterrestrials. It's a reminder of what we're capable of when we work together toward a common goal. It's a time capsule of Earth in the late 20th century, a snapshot of our world, our cultures, our aspirations. And it's a message of hope, a belief that humanity can solve its problems and continue into the future, that we won't destroy ourselves, but will endure and perhaps someday join a larger community of intelligent species in the galaxy. Whether that hope is justified, only time will tell. But Voyager, sailing silently through the darkness between stars, will carry that message forward for billions of years, long after everyone who built it, everyone who operated it, everyone who lived on Earth at the time of its creation has been forgotten. In that sense, Voyager is truly immortal, or as close to immortal as anything humans have ever created can be. Closing. And so we return gently to this moment, to this quiet time of rest. The Voyager spacecraft continue their journey, even now as you listen, every second carrying them thousands of miles farther from Earth. They are out there in the darkness, two tiny machines built by human hands, traveling through a realm no human will likely ever visit, returning faint whispers of data about the universe beyond our solar system. There is something comforting in knowing that Voyager is out there. These small emissaries, carrying our greetings and our music, our images and our hopes, are still traveling, still functioning, still sending back their messages. They are proof that we can accomplish remarkable things when we work together, when we apply our ingenuity and our persistence to a great challenge. As you rest tonight, you can imagine Voyager out there in the cosmic ocean. You can picture it moving silently through the space between stars, its instruments measuring the plasma and magnetic fields, its radio transmitter sending a faint signal back toward a pale blue dot that, from Voyager's perspective, is lost in the glare of the sun. Or perhaps Voyager has gone silent by now, its power finally exhausted, and it travels on in darkness, a ghost ship sailing through an infinite sea. Either way, Voyager's journey is not done. It will continue for billions of years, a testament to a species that wondered about the universe and dared to explore beyond the boundaries of their small world. And in that journey there is a lesson for all of us, that curiosity, courage, and the willingness to reach beyond ourselves can lead to extraordinary achievements. That the universe is vast and beautiful and full of wonders, and that we, tiny as we are in the cosmic scale, are part of that universe, connected to it, able to understand it and marvel at it. Rest easy tonight, knowing that Voyager continues its lonely voyage, carrying a piece of humanity into the cosmos. Let that thought bring you peace. Let it remind you that we are part of something far larger and older than ourselves, that our existence is brief but meaningful, that the universe is sublime and terrible and wonderful, and that we have the privilege of being here, conscious and aware, able to contemplate these vast mysteries. If you've enjoyed this journey through space and time with Voyager, please consider subscribing to the Science Pillow and turning on notifications so you won't miss future explorations. Give this video a like if it helped you relax or taught you something new about these remarkable spacecraft and their incredible journey. And feel free to leave a comment sharing your thoughts about Voyager or suggesting topics you'd like to hear about in future videos. Thank you for spending this time with me, exploring the story of Voyager's lonely voyage through the cosmos. Until next time, rest well, dream deeply, and remember that somewhere out there, Voyager continues its endless journey into the night.